feel free to record this talk. Yeah, it's totally fine to record it. And thank you so much for the invitation, and thanks for the great workshop. So this work is with my great collaborators. These are, I mean, yeah, all of the work is basically done by my collaborators. Uh, yeah. So let me introduce them. So Xiaowen Chu, who is my postdoc, and whose work who has been working on unconventional superconductivity, and all the work on non-Fermi liquid is done by in collaboration with Professor Asad and Bimla and Johannes and Professor Vojta. So let's get started, and feel free to stop me if there are some confusing aspect, which is like some pressing issue. But if there's some more detailed question, you may ask at the end. So let's get started. So I won't be looking at the chat. So if you have any question, just unmute yourself and ask, because it's hard for me to look at the chat. So that will be great. So let me just start from the so the first part of my talk will be on unconventional superconductivity in correlated systems, and there's very kind of I don't have to say much to motivate this topic, because it's such a big field in itself from this experimental point of view. As you know, high temperature superconductors, they host this a D-wave superconductivity, and then they are just so many materials which are heavy fermion materials, which have unconventional superconductivity. And perhaps much more relevant to this talk will be systems which are Mott insulators close to unconventional superconductor. So these are often so they're a large class of materials in which goes by the name of organic Mott insulators, and there are tons of them, and they often so they are at half filling, and they have a Mott insulating face, which you can tune superconductor by pressure. So these kind of systems. This is the kind of phase diagram. So the question is, can one write down models which capture at least some of this physics? So what would you like? We would like a model which has Mott physics, so that you can localize electrons like a repulsive Hubbard U, and we would like it to have unconventional superconductivity, and we'll also perhaps like some competing order, perhaps like antiferromagnet, like here. So if you look at this phase diagram, there's antiferromagnetic insulator, next to it is unconventional superconductor, and separated by a Mott transition. So this is the kind of thing we are aiming for. So why is this a hard problem? This is a hard problem, which you're already in this workshop, so I don't have to say this, but you by now know that there's this infamous sign problem that makes it very hard to do this. So that's why if you take, for example, high TC phase diagram, which is, if you try to think of, at least try to write in a model such as Hubbard model, like in this case, it has a sign problem as a function of doping. So at any non-zero doping. So that makes it really hard. So the essence of sign problem, at least for the way I see it, looking at, if I put all the examples together at some level, the essence of sign problem is that there's a tension between repulsive on-site interactions, which one can call Mottness, and having a Fermi surface. And Fermi surface, I mean, yeah, like where there's a finite density of charge, of electron charge, along a whole surface, not like a point, but a whole surface where electrons remain gapless. So that's the hard part about sign problem. So so what is the way out of sign problem? So there are many models which don't have sign problem, and that's what we mostly work with. So you can call them designer Hamiltonian or or designer Hamiltonian, where the sign problem goes away. So very broadly speaking, this is just like a one way to categorize all these Hamiltonians together is in this format. So you can kind of try to classify in two different classes, at least conceptually. It's a useful way of doing it. If you want mod physics, then you can do it, but then you don't get Fermi surfaces. Then what kind of stuff can you get if you want mod physics? So you can get you are restricted to half filling and bipartite lattices. At least that's a fair statement. So one class of problems, perhaps, if you have half filling and bipartite lattice, I mean, the most simplest thing you can do is, like, for example, square lattice. Then you will have some nesting, for example, if you don't put any pi flux, and immediately this will become unstable to any kind of repulsive Hubbard interaction. So you will get a antiferromagnetic insulator which has mod physics, but you don't get Fermi surface then. So you have to give up on that. Or other class of problems you can study, which are more interesting at some level, are Dirac semi-metal competing with antiferromagnets. So then you again don't have Fermi surface, but you have Dirac points which are stable to weak repulsive interaction, and then you have they become unstable to perhaps some antiferromagnetic order at some finite critical Hubbard Q. So as I said, okay, you can't have mod physics and Fermi surface at the same time. So as you see from here, but let's say you want Fermi surface, then what do? Then you have to give up on mod physics. So these models are often formulated as multi-band Hubbard models with perhaps interband repulsion, but on-site attraction. So you can write down such models where there is Fermi surface, and can capture a lot of competing orders. For example, nematic spin density wave and no nodal superconductor. So that's kind of crucial. It's basically impossible to get nodal superconductivity within this framework of attractive attraction. So what do you give up here? You give up mod physics, and much more importantly, often there will be a S-state superconductivity lurking at low temperature. Because you have on-site attraction, so things like to bind up, and you basically essentially at ultra low temperature, it's physics of S-phase superconductor, which is not super important most of the time. There are cases where it could be interesting, but at least that's not I am focusing in this talk. So going back, as I mentioned, my interest here would be, as I mentioned, mod physics, nodal superconductor, and antiferromagnet together. So we will have to stick with this part. We won't do this in this part of the talk. So and the key point is neither the nodal superconductor nor antiferromagnetic insulator require any doping. So don't think about then high TC where you have to dope to get things. You can get around it. If you're only interested in these two phases, then we don't have to do any doping. We can stay at half filling. So the question is, can you write on some model which has these phases? So there's one very interesting model which I became familiar some time ago, which is this work by Farker, Amada, and Douglas Calapino, where they study this model. HT plus HU is just a Hubbard model, repulsive Hubbard model at half filling on the square lattice, and then there is a term which is a square of kinetic energy for each bond, and they found some signal of D wave superconductor, but the signal was weak. I think it's fair to say, because the order parameter was quite small, and it is hard to do as far as I can tell. I mean, even on the larger system size, so this is 1 over L, it's not as kind of, I would say, I mean, if you want to really extrapolate to thermodynamic limit and perhaps study even the phase transition, it won't be very easy with just this much. Maybe you can do better. Now maybe we can revisit this model, that'll be nice. But we were thinking, so this was a good motivation for us to perhaps think of other models which may have similar physics, but perhaps where the signal is larger. So what we did was following. We took the Hubbard model, HT plus HU is just the Hubbard model on the square lattice without any pi flux, nothing, just normal nearest neighbor hopping on square lattice, so that if there is only this term, you will just get antiferromagnetic insulator at any non-zero u. But then we modified it with additional terms. So I'm changing now the Hilbert space. I introduce an extra variable theta on the bonds. So the Hilbert space is conduction electrons on each vertex and a fluctuating phase on each bond, theta ij. And for this theta ij variables, I just write down the standard xy model. So xy model, if you recall, is just the kinetic energy for this rotor's theta, which is n square. N and theta are canonically conjugate, and this is just the xy term. And then you couple this theta variable to the to a fermion bilinear, which is essentially just the d wave order parameter. So so the one way to think about this theta variable is that e to the power I theta is like fluctuating Cooper pair. That's one way to think about this. So this model, although it looks a bit contrived, but it has all the same symmetries as the conventional Hubbard model. It does not break any symmetry explicitly because it has a charge conservation. Theta variables are now charged under the global charge conservation U1. So under as you know, if it were just Hubbard model, C goes to C e to the power I phi is a symmetry, and so it is here also. You have to just act on theta with also the same symmetry to recover your charge conservation. As I mentioned, e to the power I theta you can think of as something like CC, C times C. So this is like a 4 fermion term essentially in this, but I'm writing in a way so that it kind of separates out these things, the fluctuations. So and taus are just some numbers. So basically they are there to give you the nodal d wave which we wanted. So that's the model. If there are any questions about the model, please ask, because this is kind of important. Otherwise, I will proceed. Okay, so let me keep going. So you can argue quite convincingly that this model, when in certain limit, and you can think about it yourself later, but you can argue without any numerics, it will hold a nodal d wave. Because basically, if you condense theta, go to a limit where theta is condensed, where j is large compared to k, and first, for example, set v to 0, then turn on a little bit of v just by usual, because you have broken the symmetry, v will automatically, theta become like a number in that limit, and perturbation theory converges and all that. So there's a finite radius of convergence, and in that regime, we'll get nodal d wave. And of course, we already know how to get antiferromagnetic insulator if you set, for example, g and k to be small. So this is a mean field phase diagram you will get. So you get a nodal d wave superconductor in a large part of the phase diagram. So the as a function of k over j and u over t, and then there's a antiferromagnetic insulator. Perhaps interestingly, there's an intermediate phase where there's a coexistence of gapped d wave superconductor, which I just mean you gap out the nodes, but you retain basically the pi over 2 rotation symmetry of the d wave, and then in the momentum space and antiferromagnet coexisting. And it's not like phase separated or anything. Both things are broken at the same time. There are 2 order parameters in this phase. So there's no like there's no phase separation. And the physics of this intermediate phase is that the nodes in this, because of the symmetries of our Hamiltonian, the nodes are pinned in a way so that their separation is pi pi, the node between the nodes in the nodal d wave phase. So you can imagine condensing a Néel vector, which is also lives at pi pi, the antiferromagnetic order parameter. So as soon as Néel order parameter condenses, it gaps out these nodes. So that's the physics of this intermediate phase, where it does not destroy the superconductivity. And this is the actual Monte Carlo result. So this is the 1 over L scaling of the d wave order parameter, as I earlier promised. And this model, there's really no ambiguity. You just basically, you just know it is there. You constructed it that way to get d wave, and it's a large signal, and you get d wave, nodal d wave. and you also get antiferromagnetic order in some other regime. So I will show the, so what we will do is to tune actually, maybe I put the phase, so this is basically the phase diagram. So in the actual Monte Carlo. So we keep, for example, all the other parameters fixed. Let's say set V to 0.1. V is the coupling between bosons and this fermions. Set V to be 0.5 and fix UNT to some numbers, but only tune K over J, which is the, so when, as recall, when J is large, you try to condense the this fluctuating Cooper pair. So when J is large, which is this regime, you get nodal D wave. When J is small, you get antiferromagnetic insulator. So we just tune one parameter to get the three phases.
Tarun,
Yes.
I have a question. Can you go back one?
Yes.
So the no one forward, the Monte Carlo, the Monte Carlo results. If you go, yeah. So that's okay. So you have, so essentially, how did it happen? You have a Gauss-Never transition between a D wave and.
Yeah, I'm coming to the transition in just 1
okay.
minute. That's
okay.
yeah, that's in fact the second part. But if the question is about transition, it will be get addressed in just 1 minute.
Okay, so I'll wait. Perfect.
Yeah. So the but let me, I want to say one thing. I really feel like emphasizing one thing, that it's not surprising that we get nodal D wave. We constructed model in this way. The surprise, it does not have sign problem. That was a surprise to us because we really thought it will not be possible. We were playing with a completely different model on a completely different lattice. We were studying something about deconfined criticality and so on, and we found it, and we suddenly noticed one day, oh, this, we can also do this, and then we didn't do any of that. We just focused on this because it looked kind of very fun. So anyway, so then so now there are two transitions. The transition between gapped D wave, I mean this coexistence phase where there's a gap D wave and the AFM to AFM is just 3D XY, because all the action is happening in the charge variables. Antiferromagnetic exists on both sides. So this is just 3D XY, and that you can just show. So I even deleted that slide because it's so obvious that it works out, all the exponents work. So the more interesting transition is this transition from nodal D wave to this gap D wave plus AFM. So how does that work? So you can do scaling and you get some exponents for that transition. Nu is 1, eta is 0.55. So what is the field theory? So let's try to think in terms of just normal, like as condensed matter physicists, we like some continuum description of things. So this was studied long ago, this transition. Not for this model, but for a complete, I mean, just phenomenologically it was studied for a different reason, but things just carry over pretty much. So this is work by Leon and Matthew and Chetan long ago. So how to think about this? So what is a low energy theory? At low energy theory, you have Dirac nodes, and you also have a fluctuating Néel order parameter, and you couple them based on all the symmetries, do the expansion around, do the just low energy field theory, you get this action. And you see it clearly breaks because the charge U1 is broken on both sides, because this is superconductor, this is also superconductor. So that reflects in the psi-dagger coupling. And if you do just particle hole transformation on the psi, let's say take psi up to psi-dagger down, this will now look like psi bar psi, but this will look like psi bar if you just do normal particle hole. So that looks a bit funny, and that's how they wrote down the action in this paper. But then we looked at the RG, and it looked like identical to Gros-Neveu. So that made us think, okay, maybe this is Gros-Neveu. So what we did was we thought a bit more, and it realizes because the free part of the Dirac has actually an OH symmetry. Because if you write in terms of Majorana fermions, this doesn't have OH symmetry, the full thing, but the free part does, and you can use generator of that OH in this way. So you can do an interesting particle hole transformation, which is, I don't know what to call it, just Boglikov transformation of some kind, this kind of transformation, and you get this action. So you map it to Gros-Neveu transition, and that wasn't okay. That to us that was kind of interesting that we could do it, but so this is the answer for the field theory. You get Gros-Neveu, and this one is very well studied because then all the results are tabulated up to fourth order epsilon expansion, all this numerics. I don't know, Parker, and there's it's like 20 papers on this in last 10 years. So it's, a lot about this transition, and the numbers we get are consistent with past results. Of course, there's a spread in all numerics, all epsilon expansion, but it's within that range. Does it answer the question, Parker?
Yes, it does. It does. Yep. Thank you.
And there's a recent paper by Otsuka and collaborators where they studied a different model which doesn't actually have a charge U1. They explicitly break it. They just consider BCS mean field and Hubbard U. So this model doesn't hold a conventional, doesn't have a superconductor in a true sense because they have broken the symmetry which gives you superconductor explicitly, charge U1. But this is still an okay model to study this transition. If you think about low energy theory of our transition, you will recover from this model also. So you won't get our phase diagram, but if you're just interested in this specific transition, you can recover it from this because the charge U1 is explicitly broken on the both sides of this transition. So that's fine. Anyway, I thought I should mention this because this paper came out around the same time as our paper. So yeah. So, and you can also try to study velocity renormalization. There's a prediction from field theory that all the velocities become equal. So there are three velocities: Fermi velocity, the spin wave velocity, and the superconductivity velocity, whatever. The V delta, which is the superconducting gap. If you take a cut along zone, then it's V delta is like delta essentially. So like, Dirac node has, depending on which direction looking, it is either VF or V delta. So it's anisotropic. But the prediction is should look more and more isotropic as we approach transition. In a small system, it's hard to see this RG, but we still see some evidence that things seem to approach each other at this transition. But it's not very conclusive, but I think at least this hasn't been tried before in other contexts. So it was fun to see that at least some of it seems to work. But the RG flow is typically very slow for velocity. So it'll be good to pursue this at bigger sizes.
What are fit 1 and fit 2?
So there are two kind of fits we did. So because of there's a large curvature close to the Dirac cone. Sorry, I should have mentioned. Yeah. So the Dirac cone has a large curvature. So if you I skipped the slide. So this is the various cuts along the Brillouin zone to see the Dirac to see that nodal. So depending on it's just a technical thing. There are two ways to derive the velocity. Either I don't know. You can look at this point and do some way, or you can look at 3 points. It's basically something like that. I can go into detail, but it's not very important. So, but it's because we have just few points, so it's hard to kind of extract something which is. There could be many schemes. So you can look in the last page of the paper in the appendix, which discusses these two things, but they don't give very different results essentially. So I have maybe 5 more minutes. Is that? I think it's 1:29. We started at 1:05, so it has been.
Yeah, it was actually even a bit later, so you have closer to 10 minutes.
Okay, thanks. So the second part of my talk, as I mentioned, is work with Farker, Bimla, Johannes, and Matthias Voita, and it also builds on previous work with Toshihiro. So what is the motivation for this part? So the broad motivation is new phases of matter in the context of heavy Fermi liquids, or in general Kondo physics. So there's this beautiful experiments where this paper where experimentalists studied cobalt atoms on a metallic copper. So cobalt is magnetic, copper is metal. So you can almost like building Kondo lattices from scratch. So this is also a designer Hamiltonian, but they are not trying to get it a sign problem. They're really designing things in a true sense. So there's a very nice work by Bimla, Farker, and Frederick Miller on trying to provide evidence that this experiment can in fact be modeled by a Kondo lattice. So what kind of Kondo lattice it is? That's a nice part. It's a new kind of Kondo lattice Hamiltonian. You're coupling a two-dimensional system. So C dagger I Cj, this is really a two-dimensional Hamiltonian describing the substrate layer, this copper layer. But the atoms are one-dimensional. But they're also coupled to each other by Heisenberg coupling. And there is a magnetic field which we'll neglect in this talk. So that is the interesting result. And so this is a Kondo coupling between the conduction electrons and the local movements. So it's not like a single impurity Kondo problem where there's just one thing, one magnetic atom. Neither it is a conventional Kondo lattice Hamiltonian where electrons and the local moments live in the same dimension. So that's interesting. And there's another motivation, which maybe I don't have time, but there's another material, which is a three-dimensional metal in which people have seen evidence of spin-ons. This is this ytterbium platinum tin, and then it has this not tin, sorry, what is PB? Lead, sorry, yeah. So they see evidence of spin-ons, like one-dimensional spin-ons along various lines in 3 dimensions. That's very interesting. And again, there should be Kondo coupling, but they don't see any Kondo effect of any Kondo coupling. Okay, so that's interesting. So overall, we were motivated about this competition between one-dimensional physics, where in 1D spin-ons propagate, and the physics of heavy Fermi liquid, where spin-ons basically disappear and all the magnetic localized, these localized moments get absorbed in the metal, like in a normal heavy Fermi liquid. So this is the tension we want to explore, this kind of these two regimes. So again, we want Mott physics because we want localized atoms. So we are restricted to, at least in this paper, we were restricted to this. We can also do more things, but so the model we study is basically we put a bottom layer conduction electrons on a pi flux core lattice, so you get Dirac fermions, and then just do Kondo coupling and just the Heisenberg coupling also of the local moments. So the Kondo coupling between local moments and conduction electrons, and Heisenberg coupling between the magnetic atoms. So then you can write down a low energy field theory. And so I'll focus more on the field theory part because there's a lot to be said about just the numerics, but I felt like focusing on this because it's kind of a different kind of a transition where you live in 2 different dimensions. So this is Dirac Hamiltonian in 3 dimensions. This is the Kondo coupling, which is in 1 lower dimension. You see this is d2x, this is dx. And you can study the RG and you get this RG flow that there is a actual intermediate strong coupling fixed point as a function of Kondo coupling. So that's an interesting result. So there is a decoupled spin chain limit where spin-ons exist. They dynamically decouple from conduction electrons. And at large Kondo coupling, they get absorbed. This is like a heavy Fermi liquid phase, if you like. And then there's a Kondo breakdown critical point, if you like. So that's the main result. And you can do RG, and consistent with this, that's what you find. So I can't get into details because I have limited time. But and all of this is borne out by the actual Monte Carlo numerics. At small value of the Kondo coupling, you do find up to some critical point, you find spin-ons exist, and then they disappear after that. So very much, like this experiment I mentioned, spin-ons exist, or this experiment, okay, it's not, maybe more work can be done to tune this coupling, but and also it's a metal there, not a semi-metal. So this is all the stuff is consistent. So let me not move ahead. Is again, you can see the hybridization vanishes in this regime at small Kondo coupling up to some critical value. This is think of it as like a hybridization between the conduction electron and the local moments. And so in this example, so you can think of this Kondo breakdown phase where the spin-ons exist as a small Fermi surface phase where the local moments do not get absorbed in the semi-metal. So this is a very timid version of what is called fractionalized Fermi liquid. Timid in the sense that its effect is sub-dimensional. It's only one chain on some two-dimensional system. It doesn't get absorbed, so it doesn't change macroscopic properties. Only changes things close to the chain. So so the question is, can you find more regular versions of fractionalized Fermi liquid where conduction electrons and local moments live in the same dimension, not this dimensional mismatch, and it's still fractionalized Fermi liquid? So this is work with Johannes. So this looks like a bit of a monster for Hamiltonian, and it's a heroic effort by Johannes that we could simulate this. So there's the Hamiltonian has three parts: conduction electrons, just usual hopping; Kondo coupling, which is with funny-looking Kondo coupling. It's a minus 10 to the power x. This is what we need to do to get rid of sign problem. And most interestingly, interaction between the spins is chosen in a way so that you get fractionalization of spins into a Z2 spin liquid. So it has topological order, like very much like toric code, the same kind of topological order that exists in toric code. You can think of, if you want to think very simply, think of this as the toric code part, and you're coupling the toric code. But it has a U1 symmetry, which is important for us. Toric code doesn't have U1 symmetry to do Kondo coupling. Anyway, so this is the model. Again, if you don't, get into details, just broadly point of view, coupling a topological spin liquid to conduction electrons, and this is the phase diagram looks like. So there is a regime in which this spin liquid exists, coexisting with this conduction electrons, which form a semi-metal, because conduction electrons live on some honeycomb lattice. These red dots and the blue dots, A and B sublattice of honeycomb, and the localized moments live on some Kagome lattice. So the physics is basically you get a phase of matter which violates Luttinger theorem, because the conduction electrons do not get absorbed into the semi-metal's Fermi surface. So the picture of this is basically you have conduction electrons are doing their RVB motion, and the local moments are doing their RVB motion, and the conduction electrons basically decouple. So conduction electrons move around, and you can study this transition from an entanglement point of view and look at the decoupling between these two theorem using entanglement. You can do other things also. So I don't have much time, but let me just finish on this one last point about the transition. So there's this fractionalized Fermi liquid where there's topological order, but also it's a metal also. So it's like a metallic, it's like a gapless topological phase. You can ask, how does that get destroyed to a magnetic insulator, which is a kind of a trivial phase in some sense because it doesn't have any topological order. So you can ask what happens at the critical point. And the interesting result is that at the critical point, also you find these two things continue to decouple, these two sectors of charges and spins, precisely because of fractionalization. So because of the fact that the localized moments have topological order in this phase, their anomalous dimension eta is bigger than 1. Generally, it's to be, in a normal system where, think of some 3D critical point, Wilson-Fisher critical point, eta is like 0.03 or something like that. But here eta is actually 1.3 or something at this critical point for the localized moments. So that's why this Kondo coupling, if you do RG, Kondo coupling become irrelevant even at the transition, precisely because eta is bigger than 1, the anomalous exponent of the spins because of fractionalization. So that makes this Kondo coupling irrelevant. Basically, if spins are so much broken apart that electrons are having a hard time coupling to them. So that's why Kondo coupling remains irrelevant even at the transition. And this was studied long ago with Senthil in my PhD thesis, but it was interesting that it came back in this project. So so the broad message is that it's problems which sometimes seem very hard. Sometimes there are workarounds. You can find sign problem free models which capture some of the physics we are interested in. Maybe you won't get everything. You won't get Mott physics in a Fermi surface so far. That sounds perhaps almost impossible from at least from some considerations, but you can get some other things which are still interesting, like Mott transition between superconductor, between unconventional superconductor, antiferromagnet, non-Fermi liquids. So one question, maybe out of all this, you can read all this, but it's anyway being recorded. You can look at it later. But one question which is interesting is, can you dope our model, this unconventional superconductor? Because a small doping causes a small problem in DMRG, at least looking at the past results on Hubbard models. So if you're already in the regime where there is a superconductor, if you dope it a little bit, perhaps you can access the part of the high TC phase diagram, like in cuprates, which is at large doping by just a little bit of doping in our model, because we're already in the nodal part. Okay, this is just a fantasy. I don't know whether it's possible, or maybe I'm just misguided, but this is something which might be interesting to think about. Yeah, I think that's about it. I should stop. Yeah. Thank you.
All right. Thank you very much, Tarun, for your talk. Do we have questions?
I have a question, Tarun, still.
Yeah.
So for the first part of the talk, do you always find coexistence, or do you find also phases? You know, you can change U essentially, right? I think you still have this parameter in your. Or do you always find coexistence, or do you find first order transitions, or? I mean,
so far we in all the regime we explored, we never found a first order transition. Because just I don't know, it's one of those things where there's sort of nesting, so
right.
it likes to be very much like gross niveau. So as far as we can tell, I mean, we didn't obviously explore the all possible cuts. We are doing one cut here. Yeah, one can probably explore more. What we were trying earlier, and that we can argue based on Barry phase that it can't happen in this model. We have a different model where it does happen, and that's what we were originally studying. But then we thought maybe you can have a new kind of deconfined criticality where there are nodes. No one has that. That won't be CP1 model or anything like that. It will be some completely new kind of phenomena. But we now believe it can't happen in this model because of just the way Barry phase works out. So that's why there's always this thin sliver. Even when K is very large, it is all mean field, obviously, but it seems to capture what we'll find in actual Monte Carlo. It's almost looks like second order transition because it becomes very tiny, this regime, the coexistence regime. But the short answer is as far as we could tell based on the parameters we explored, we did not find a first order transition so far.
Yeah,
were you expecting it to be there? What was your?
No, I mean, I would expect it. No, I would not expect it to be there necessarily. I just, just would be interesting to see. I mean, the experiment you were showing had a first order transition, right?
Exactly, because I think so. I talked a little bit with Kondo. Okay, this should be offline, but I shouldn't mention what we talked. But it just, I don't know. What I learned is that it's
recording if you
it's sorry.
I can stop the recording if you prefer.
Yeah, maybe we can stop it. Recording.